Now we're going to talk about a theorem that's of very high importance, and it's very related to the implicit function theorem, but it's a little different. And in particular, it's kind of a specialization of the implicit function theorem. Let's start with an example. Really simple. F of x is equal to x squared. Well, this has a unique local inverse around all my x's that are not equal to 0. If x is equal to 0, I don't have a local inverse. And why is that? Well, if we look at the graph, x squared is this parabola. Goes on forever there. And of course, so this is x and f of x. The picture of the inverse is that we flip this picture along the diagonal. So if we have an inverse, right, we should be able to think of it as flipping along the diagonal. And what happens when we flip along the diagonal? Well, on this side we have a square root function, right? And here we have a negative square root. There are two kind of branches here. And so this would be, we'll say this is y, and this is f inverse of y, potentially, right? But the thing, of course, that this function is not well defined because it doesn't pass the vertical line test, right? So if I ignored one of these guys, right here, if I just considered that function, then I have a nice well-defined inverse function there. And that could be my candidate for f inverse of y. But at 0, something bad happens, right? I cannot get values around 0 for this function, right? And in particular, it's kind of useful to think about the linear approximation there, right? So so we note that f prime of x is equal to 2x. And so we note that as a matrix, f prime of x as a number, as a matrix, is invertible or non-singular or has non-zero determinant everywhere except 0. So that kind of indicates that something bad is happening, right? When our derivative vanishes, that means that our implicit function theorem is kind of failing. And the reason it fails here is because I can't get values of my inverse function if I want to get a negative y in there. And so around 0 it can't exist, right? Also note, so another example is that for a linear function, right, say g of x is equal to ax, right? Well, an inverse exists if and only if a inverse exists, right? And of course, g inverse of b is just going to be given by a inverse times b, right? It's simple to see that that is the case when a is invertible, right? And of course, this is only going to happen for square matrices. Well, in order to get to where we need to go to actually make this all work out, right? To say that, well, I can have this inverse function as long as essentially, I compute a Jacobian and therefore, and then I look at the linear problem, which is, oh well, the Jacobian needs to be invertible, right? In order to get there, I need some definitions. So definition. So recall that f from Rn into Rm is onto for surjective, if for every x in Rn, or for every, b in Rm, there is x in Rn such that f of x is equal to b. F is injective, or one-to-one, or injective. If whenever f of x1 is equal to f of x2, x1 is equal to x2. Right, so that means there's at most one solution to f of x is equal to b. Right. F of x equals b has at most one solution. Right, and we characterized when linear maps are onto or injective, right, onto or one-to-one. But now we're going to talk about nonlinear things, and we don't get global injectivity or global surjectivity. We have to talk about things in terms of local injectivity and local surjectivity. So we're going to say that f from Rn into Rm is locally onto, same as locally surjective, at x naught if given any small open ball, so like an open interval or an open disk or whatever, around x naught, there is, and we'll call this ball x, there is a small ball b around b equals f of x naught. We'll call it b naught, such that for every b in b, there is an x in x with f of x is equal to b. So that's the local surjectivity, and f is locally one-to-one or locally injective if for any small open ball around x naught, there is b around another small ball around f of x naught, such that if b is equal to f of x1 equals f of x2 for x1, x2 in x and b in b, then x1 is equal to x2. So locally, I'm only going to send one x1 to one point somewhere, and that's local injectivity. So example, right? F of x is equal to x squared is not locally 1 to 1 or onto at x is equal to 0, right? And in particular, if we have something that's locally 1 to 1 and onto, we can always invert it. There's a natural way to invert something. And of course, the reason this fails is that, you look at the number line, you look at a small interval around 0, right? And what does this map do to that interval? Right, well, it's going to go, so f of x and x here, well, it's going to go to, 0 is going to go to 0, but I'm going to have 2 points going to each of these points in a small interval around here, and I don't have anything mapping to this point, right? So that means that it's definitely not 1 to 1, and it's most certainly not onto in a small region, around any small region of 0. So that means that this is really bad at that point. So, and we have a theorem that we can state now that we have this. So suppose f from R n into Rm is C1 with f of x star is equal to b star, and let df x star denote the Jacobian. Then A, if df x star is onto, then f is locally onto at x star, x upper star. B, if df x star is 1 to 1, f is locally 1 to 1 at x star. So that means that my Jacobian is telling me local information about f, whether it's locally onto and locally 1 to 1. So global properties of the Jacobian tell me local properties of f. We have corresponding local properties. And that's kind of the beautiful thing. And using this, we'll be able to state the full inverse function theorem.